Welcome to Emtron Training Part 22. In this training tutorial, we're going to take a look at working with our speed density airflow-based modeling strategy within our programming. We're going to find that the speed density modeling will require us to have a whole bunch of variables accounted for and understanding the fundamental concepts behind how speed density works and estimating the amount of air mass that's coming into our engine. We're going to break that all down here in the tutorial, also giving you tips and tricks of how to calibrate and tune your main VE table. We're going to have a lot to cover. Let's jump in so we can check this out. Okay, so let's get started. We're going to be taking a look at working with our speed density airflow-based modeling strategy that we have within our Emtron ECU. We have a variety of different ways we can represent what the air mass or airflow is coming into our engine with our Emtron. We can use a map pressure sensor, traditional for speed density airflow-based strategy. We have a mass airflow sensor. We can use that to measure the amount of airflow coming into the engine. Then we also have throttle mass flow. That's going to be based on looking at the cross-sectional area of the throttle plate, plus taking a look at the pre and post pressure references, map pressure references, before and after the throttle plate. We're going to have a dedicated video on the mass airflow and throttle mass flow type of airflow strategies. This video we're just going to be focusing on taking a look at the speed density airflow strategy, because this is different than the other strategies we have available, and it's probably the more common of the three. You'll find that if you're working with almost any standalone from the last probably 10 or 15 years, chances are it's going to be in a speed density volumetric efficiency based strategy or some kind of a speed density based strategy. And this is probably what you're more familiar with. But we want to dig a little bit deeper into how this actually works, going in and knowing the rules of thumb in terms of the values that we place within the table. They're not arbitrary. They are going to be a little bit more specific. We're going to be talking about some ways we can calibrate and work within the table, and then just some rules of thumb when we're looking at the airflow estimation and our injector information and determining if we have, let's say we're running richer or leaner than target, determining what kind of changes we need to make, where the air lies, because we know we have an underlying equation. Fuel mass is equal to air mass divided by target air fuel. And if everything's balanced, if we have proper injector data, well then we'll convert a fuel mass into injector pulse width. And if we're representing the air mass properly, we'll find that everything will balance out, where we'll represent the air mass, we specify the target air fuel, we convert the fuel mass into an injector pulse width, and we should find that we're hitting the target air fuel spot on, and there's no deviation or difference. If we find that we're richer or leaner, then we have an error that's being introduced, and that could be either on our injector data side or on the airflow modeling side. So we can determine if there is an error and where the error lies, and we'll get into that towards the end of the tutorial. It'll be a bit more specific in terms of nailing down what that problem is, where your error is coming from. But we first need to understand the fundamentals here for working within the speed density airflow-based strategies. So let's talk about that first. So again, our equation that we have that ties everything together here in our Emtron between airflow and fuel modeling is going to be fuel mass is equal to air mass divided by target air fuel. So our job is to estimate what the air mass is going to be in this speed density based airflow strategy. If we're dealing with mass airflow, then we would measure the airflow. In this case, we're estimating the airflow. Now, in order to estimate the airflow or the air mass, we need to have an equation that's going to be tying the air mass estimation together. So let's talk about that, because that's going to be important in understanding what we're trying to accomplish here when we're actually calibrating and working within our main volumetric efficiency table. This main VE table is going to be specific to working within our speed density airflow strategy. So how we actually estimate the air mass is going to be based on a couple different variables and sensor inputs. So we'll find that air mass is going to be the equation here is map pressure times the volume per cylinder divided by the universal gas constant multiplied by the charge temperature. Now all of that will have a multiplier against the engine percentage efficiency or the volumetric efficiency. That's the values that we find in the table here. We need all of that information to be able to estimate the amount of air mass. And all of that data or information has to be accurate, or else the air mass determination will be inaccurate. So if we're breaking this down here a little bit further, let's look at each individual portions of the actual equation so we know where they're coming from and how things are represented. So looking at the equation, we have our map pressure. The map pressure sensor is going to be fitted to the intake plenum after the throttle body. That'll measure either the vacuum or positive. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.